This is a foundational textbook in the field of computer science. It explains what algorithms are, how they operate, and their limits. It places algorithms as a core technology, just like computer hardware, user interfaces, and networks. This book is widely regarded as one of the most comprehensive and authoritative resources for learning about algorithms, suitable for both academic courses and self-study for professionals. The book has 8 parts.
Part 1, called Foundations, introduces the basic ideas needed to design and analyze algorithms. Chapter 1, The Role of Algorithms in Computing, defines what an algorithm is. It's a set of precise instructions that takes an input and produces an output in a limited amount of time. The chapter highlights algorithms as tools for solving computational problems, giving examples like the Human Genome Project, the Internet, online shopping, and manufacturing. It introduces important problems like sorting, finding the shortest path, and topological sorting. The chapter also talks about data structures, which are ways to store and organize data, and briefly mentions NP-complete problems, which are computational problems for which no fast algorithm is known. It concludes by emphasizing that algorithms are crucial for system performance, and introduces concepts like parallel computing and online algorithms. Chapter 2, Getting Started, introduces basic algorithms such as insertion sort, which is a sorting algorithm that works incrementally, and merge sort, which is a recursive divide and conquer sorting algorithm. It explains how to analyze algorithms by predicting the resources they will need, typically how long they will take. This is done using a RAM model, which assumes that instructions and data access take a constant amount of time. It introduces the ideas of worst-case and average-case analysis and the concept of order of growth in running time. This is informally expressed using theta notation, which describes how running time changes as the input size gets very large. Chapter 3, Characterizing Running Times, formally defines asymptotic notation. This includes big O notation, which describes an upper limit on how the running time grows, omega notation, which describes a lower limit, and theta notation, which describes a tight limit. It also introduces little o notation for upper limits that are not tight, and little omega notation for lower limits that are not tight. This chapter also reviews common mathematical functions, such as floors and ceilings, modular arithmetic, polynomials, exponentials, logarithms, factorials, and the iterated logarithm function. Chapter 4, Divide and Conquer, goes into detail about the divide and conquer method. In this method, problems are broken down into smaller, similar subproblems, solved recursively, and then the solutions are combined. It introduces recurrence equations to describe the running times of recursive algorithms. Methods for solving these recurrences are presented, such as the substitution method, the recursion tree method, the master method, and the Acrobasi method. Examples include algorithms for matrix multiplication, including Strawson's algorithm. Part 2, called Sorting and Order Statistics, focuses on various sorting algorithms and ways to find specific elements within ordered sets. The introduction section defines the sorting problem, arranging a list of numbers into increasing order. It highlights how important sorting is in computer science and introduces concepts like keys, which are the values to be sorted, and satellite data, which is associated information that moves along with the key. Chapter 6, Heapsort, introduces Heapsort, a sorting algorithm that sorts in place with a running time of big O of n log n, using a heap data structure. It covers max heaps and min heaps, their properties, and operations like max heapify and build max heap. Chapter 7, Quicksort, presents Quicksort, another sorting algorithm that sorts in place. While its worst-case running time is big O of n squared, its expected running time is big O of n log n, making it efficient in practice. It introduces the partition subroutine, which is central to Quicksort, and a randomized version of Quicksort. Chapter 8, Sorting in Linear Time, discusses the limitations of comparison sorts, which are algorithms that only rely on comparing elements. It proves that these algorithms require at least big O of n log n comparisons in the worst case. It then introduces non-comparison sorts that can achieve linear time in specific situations. Counting sort for integers in a small range, radix sort for numbers with multiple digits, and bucket sort for uniformly distributed numbers. These algorithms use operations other than comparisons. Chapter 9, Medians and Order Statistics, addresses the problem of selecting the ith order statistic, which is the ith smallest element, from a set. It covers finding minimum and maximum elements and presents a randomized algorithm called randomized-select that achieves big O of n expected running time, and a more complex algorithm called select that guarantees a worst-case linear running time. Part 3, called Data Structures, explores various data structures used for dynamic sets. The introduction section discusses dynamic sets, collections of elements that can change over time. It introduces common operations like search, insert, delete, minimum, maximum, successor, and predecessor. Chapter 10, Elementary Data Structures, covers basic data structures, arrays, matrices, including how they are stored in row major and column major order, stacks, which are last in, first out, with push and pop operations, queues, which are first in, first out, with NQ and DQ operations, and linked lists, which can be singly or doubly linked, with or without sentinels to simplify the code. Chapter 11, Hash Tables, introduces hash tables for implementing dictionaries, which are sets that support insert, search, and delete operations. It explains direct address tables for when the set of possible keys is small. For larger sets, hashing uses a hash function to map keys to slots in the table. It addresses collisions using chaining or open addressing, including double hashing and linear probing. The analysis often assumes independent uniform hashing for an average case performance of big O of 1. Chapter 12, Binary Search Trees, describes binary search trees which support a full range of dynamic set operations. It covers the binary search tree property, in-order tree walks to print elements in sorted order, and algorithms for search, minimum, maximum, successor, predecessor, insert, and delete. Performance depends on the height of the tree, which can be big O of n in the worst case. Chapter 13, Red-Black Trees, introduces red-black trees, a type of self-balancing binary search tree. They guarantee a logarithmic height, big O of log n, through specific red-black properties, such as node colors and black height rules, and structural changes called rotations during insert and delete operations. This guarantees a big O of log n worst-case time for dictionary operations.
Part 3, Data Structures, delves into various data structures used for dynamic sets. The introduction section discusses dynamic sets, collections of elements that can change over time. It introduces common operations like search, insert, delete, minimum, maximum, successor, and predecessor. Chapter 10, Elementary Data Structures, covers basic data structures, arrays, matrices, including row major and column major order storage, stacks, LIFO, last in, first out, with push and pop operations, queues, FIFO, first in, first out, with NQ and DQ operations, and linked lists, singly and doubly linked, with or without sentinels to simplify code. Chapter 11, Hash Tables, introduces hash tables for implementing dictionaries, sets supporting insert, search, delete. It explains direct address tables for small key universes. For larger universes, hashing uses a hash function to map keys to table slots, addressing collisions via chaining or open addressing, including double hashing and linear probing. The analysis often assumes independent uniform hashing for average case big O of 1 performance. Chapter 12, Binary Search Trees, describes binary search trees, which support a full range of dynamic set operations. It covers the binary search tree property, in-order tree walks to print elements in sorted order, and algorithms for search, minimum, maximum, successor, predecessor, insert, and delete. Performance depends on tree height, which can be big O of n. In the worst case, Chapter 13, Red-Black Trees, introduces red-black trees, a type of self-balancing binary search tree. They ensure logarithmic height, big O of log n, through specific red-black properties, e.g., node colors, black height rules, and structural modifications, called rotations, during insert and delete operations, guaranteeing big O of log n worst-case time for dictionary operations.
Part 5, called Advanced Data Structures, explores more complex data structures. The introduction section continues the study of dynamic sets, focusing on advanced data structures like Fibonacci heaps, dynamic trees, splay trees, persistent data structures, and specialized data structures for restricted key universes, such as Van Emde-Boas trees and fusion trees. Chapter 17, Augmenting Data Structures, shows how to add to existing data structures, particularly red-black trees, to support new features. It demonstrates how to augment red-black trees to create order statistic trees for finding the ith smallest element, or the rank of an element, and interval trees for managing dynamic sets of time intervals and finding overlapping intervals. It provides a general theorem for augmenting red-black trees efficiently. Chapter 18, B-Trees, introduces B-trees, which are balanced search trees optimized for disk drives or other secondary storage. B-trees have a large branching factor to minimize disk accesses, with a height of big O of log n, where the logarithm base is large. It covers the properties of B-trees, how they are created, and operations like searching, insertion, which involves node splitting, and deletion. It also discusses how memory hierarchies impact algorithm performance. Chapter 19, Data Structures for Disjoint Sets, examines data structures for maintaining a collection of disjoint sets, supporting operations like makeSet, which creates a new set, union, which unites two sets, and findSet, which finds the representative of a set. It explores linked list representations and more efficient disjoint set forests with strategies like union by rank and path compression, achieving nearly linear time complexity, which is big O of m alpha of n, where alpha of n is an extremely slowly growing function. Part 7, called Graph Algorithms, focuses on algorithms designed for graphs. The introduction section introduces graph problems, defining graph size by the number of vertices, v, and edges, e. It mentions common applications like shortest paths, minimum spanning trees, and maximum flow. Chapter 20, Elementary Graph Algorithms, covers fundamental ways to represent graphs, using adjacency lists and adjacency matrices, and search algorithms, breadth-first search for finding shortest paths in graphs without weights and building a breadth-first tree, and depth-first search for exploring deeper first, classifying edges as tree, back, forward, or cross edges, and building a depth forest. Applications include topological sorting of directed acyclic graphs, also known as DAGs, and finding strongly connected components. Chapter 21, Minimum Spanning Trees, explores algorithms for finding a minimum weight spanning tree in a connected, undirected graph. It introduces a general greedy method and two specific algorithms: Kruskal's algorithm, which adds the lowest weight edge connecting two distinct components, and Prim's algorithm, which grows a single tree from a root by adding the lowest weight edge connecting to an isolated vertex. Both are greedy algorithms. Chapter 22, Single Source Shortest Paths, addresses finding shortest paths from a single starting point to all other points in a weighted directed graph. It discusses negative weight edges and cycles, noting that shortest paths cannot contain negative weight cycles. The core technique is relaxation of edges, which updates estimates of the shortest path. Algorithms include the Bellman-Ford algorithm, which handles negative weights and detects negative cycles, and Dijkstra's algorithm, which requires non-negative weights and is faster with priority queues. It also shows how these apply to difference constraints. Chapter 23, All Pairs' Shortest Paths, focuses on finding shortest paths between every pair of vertices. It presents dynamic programming algorithms based on matrix multiplication using repeated squaring for big O of v cubed log v, and the Floyd-Warshall algorithm, which takes big O of v cubed time. It also covers finding the transitive closure of a directed graph. For sparse graphs, Johnson's algorithm provides a faster alternative, taking big O of v squared log v plus ve time by reweighting edges to use Dijkstra's algorithm. Chapter 24, Maximum Flow, introduces flow networks, which are directed graphs with edge capacities, a source and a sink, and the maximum flow problem. It defines flow conservation and the value of a flow. The main method is the Ford-Fulkerson method, which repeatedly finds augmenting paths in a residual network and uses them to increase the flow. The crucial max flow min cut theorem states that the maximum flow value is equal to the minimum cut capacity. The Edmonds-Karp algorithm is a polynomial time implementation of Ford-Fulkerson. An application is finding a maximum bipartite matching. Chapter 25, Matchings in Bipartite Graphs, explores matchings in bipartite graphs, where vertices are divided into two sets and edges only go between sets. It revisits maximum bipartite matching with the more efficient Hopcroft-Karp algorithm, which takes big O of v to the power of 1/2 e time. It also examines the stable marriage problem, which is about finding a stable pairing based on preferences and is solved by the Gale-Shapley algorithm, and the assignment problem, which is about finding a maximum weight perfect matching and is solved by the Hungarian algorithm. Part 7, called Selected Topics, covers a selection of advanced and specialized algorithmic topics. The introduction section introduces various topics, including parallel computing, online algorithms, matrix operations, number theory, string matching, machine learning, NP completeness, and approximation algorithms. Chapter 26, Parallel Algorithms, extends the algorithmic model to parallel algorithms, specifically fork-join parallelism. It introduces work, which is the total sequential time, and span, which is the longest path in the computation graph, as ways to measure efficiency, and the concept of parallelism, which is the ratio of work over span. It shows how to make algorithms like matrix multiplication and merge sort run in parallel using spawn and sink keywords, discussing race conditions and greedy schedulers. Chapter 27, Online Algorithms, focuses on online algorithms where input arrives over time, in contrast to offline algorithms that know the full input in advance. It uses competitive analysis to compare online algorithms to optimal offline ones. Examples include the waiting for an elevator problem, maintaining a search list with the move to front heuristic, and online caching, discussing deterministic and randomized algorithms like marking and how they compare to an oblivious adversary. Chapter 28, Matrix Operations, covers efficient algorithms for matrix operations. It shows how to solve systems of linear equations using LUP decomposition, where PA equals LU, meaning P is a permutation matrix, L is a unit lower triangular matrix, and U is an upper triangular matrix, using forward and back substitution. It proves that matrix multiplication and matrix inversion are computationally equivalent. It also discusses symmetric positive definite matrices and their use in least squares approximation for curve fitting. Chapter 29, Linear Programming, introduces linear programming, where the goal is to find the best value for a linear objective function while following linear constraints. It presents the standard form of a linear program and discusses how various problems, for example, shortest paths, maximum flow, minimum cost flow, multi-commodity flow, and the Poliscal problem, can be set up as linear programs. It also covers the concept of duality, where a maximization problem has a corresponding minimization problem with the same best objective value. Chapter 30. Polynomials and the FFT explores operations on polynomials, particularly multiplication. It compares coefficient representation with point value representation for polynomials. The core of the chapter is the fast Fourier transform, or FFT, an algorithm that computes the discrete Fourier transform, or DFT, and its inverse in big O of n log n time. The FFT allows multiplying two polynomials with a degree limit of n in big O of n log n time by converting them to point value form, performing pointwise multiplication, and then converting back to coefficient form. It also illustrates FFT circuits based on butterfly operations. Chapter 31. Number Theoretic Algorithms reviews basic number theory concepts like divisibility, prime numbers, composite numbers, and modular equivalence. It presents Euclid's algorithm for finding the greatest common divisor, methods for solving modular linear equations, and modular exponentiation using repeated squaring. It highlights the Chinese remainder theorem and the RSA public key cryptosystem, which relies on large prime numbers. The chapter concludes with the Miller-Rabin randomized primality test for efficiently finding large prime numbers. Chapter 32, String Matching, addresses the problem of finding where a pattern string appears within a text string. It covers the naive string matching algorithm, the Rabin-Karp algorithm, which uses hashing, string matching with finite automata, the Knuth-Morris-Prag or KMP algorithm, which uses a prefix function, and suffix arrays, which are a data structure for efficient string searches and related problems. Chapter 33, Machine Learning Algorithms, introduces fundamental machine learning algorithms. It covers k-means clustering for grouping similar items, multiplicative weights algorithms for making predictions based on expert advice, and gradient descent for finding local minima of functions, which is an optimization technique crucial in many machine learning models. Chapter 34, NP-completeness, discusses NP-complete problems, problems for which no fast algorithm is known, and if a fast solution for one were found, it would mean a fast solution for all of them. It introduces concepts like decision problems versus optimization problems and polynomial time reductions, which involve transforming one problem instance into another to prove how hard it is. It proves several classic problems, for example, circuit satisfiability, 3CNF satisfiability, click, vertex cover, Hamiltonian cycle, subset sum, and the traveling salesperson problem. Chapter 35. Approximation Algorithms presents approximation algorithms for NP-complete problems that aim to find solutions that are close to optimal in polynomial time. It defines the approximation ratio, which compares the approximate cost to the optimal cost, and different types of approximation schemes, for example, polynomial time approximation scheme and fully polynomial time approximation scheme. Examples include algorithms for the vertex cover problem, the traveling salesperson problem when the triangle inequality holds, the set covering problem, max 3CNF satisfiability, and the subset sum problem. All right, that brings us to the end of the introduction of this book. Thanks for tuning in. We hope you found it helpful.